Okay, so let's continue our discussion. So in the last lecture, we were looking at frequency response of linear circuits. And today we continue with that discussion and look at one of the applications of linear circuits, which is filtering. And so before we do that, let's just go over what we did in the last few lectures. We said that given a circuit, linear circuit, like the one shown over here, an RC circuit, we can characterize this particular circuit by exciting it with a sinusoidal signal and looking at the sinusoidal output. And the ratio of the output versus input is what we call as the transfer function. And in this case is the ratio of two voltages, but it can be ratio of two currents or a ratio of voltage and current or a ratio of current and voltage. So output could be current or voltage and input could be current or voltage. And we said that we do this analysis or calculation of transfer function by transforming the circuit into a phasor circuit where we replace resistor stays as a resistor, capacitor becomes 1 by j omega c, and then we do a normal our usual ways of analysis, mesh, nodal, Thevenin's, Norton's, all of those things, superposition, all of those things are valid. And using any of those techniques that we have studied earlier, we derive a transfer function, which is a ratio. The reason why we do a ratio is because it's a linear circuit, output is proportional to input. So the absolute value of output doesn't really matter, it's the ratio of the output and input which characterizes the circuit here. And we said that once you obtain the transfer function, then there are two things that we look at. One is the magnitude of the transfer function. The other one is the phase of the transfer function. And the magnitude of the transfer function, we take 20 log of this magnitude and we plot it on a dB scale here. And to show and to see the entire this transfer function, we look at it over a large frequency range, and therefore we plot frequency on a log scale here. And so that's the plot that we get, and we call that as a Bode plot of the transfer function. So so the transfer function is important, obviously, because that represents the characteristics of the system. And given a circuit, we would like to sketch what is the, for example, this magnitude plot here. How does the magnitude of the transfer function, magnitude in dBs versus the frequency, how does it look like? And let's look at a simple way of arriving at this particular diagram here, right? So let's say we have done the analysis and we've obtained a transfer function which is expressed in this particular form here, right? So remember, so we take the magnitude of it and we take log of it and multiply it by 20 to get a value in dBs here. Right, so let's say the transfer function is the ratio of voltages, so that's why we are taking 20 here. And so it's easy to write this out. It becomes 20 here, 10 becomes 20 here, and then minus log 10, 1 plus omega by 10 to the power 3 here, and 1 plus omega by 10 to the power 4 here. We obtain that. So this is how we're going to plot it out. This is in dBs here. And the frequency, we've taken a large enough range here. Look at it from almost like 1 radian per second to almost like 10 to the power 7 here. So let's plot this out. So once you write it out, the magnitude part in dBs in this particular form, you can take each particular term that you see here, this first term and the second term and the third term, and you can separately sketch it out as to what it would look like. So the 20, of course, is a straight line here. So the first term is independent of frequency, is a constant here. The second term, if you look at it, for frequency omega considerably smaller than 10 to the power 3, this factor is negligible and log of 1 would be practically 0. So it starts off with 0 dB here. And then this term begins to depart from 0 dB when omega starts to become comparable with 10 to the power 3. So omega at 10 to the power 3 or beyond. So a simplified sketch of this particular term here, let me emphasize, a simplified sketch is we keep this term as 0 up to 10 to the power 3. Note that if I put omega equal to 10 to the power 3, I'll get log of 2. So it's not really 0 here, but I'm emphasizing that we are doing a simplified sketch here. Okay, so we keep it 0 dB till omega becomes equal to 10 to the power 3. Beyond that, Beyond that, as we have seen in the last lecture, if omega is much larger than 10 power 3, then the slope of this particular line is 20 dBs, minus 20 dBs per decade here. Because if you neglect 1 and if you increase omega by a factor of 10, then because there's a square also, so the value of the magnitude changes by 20 dB here. So the second term then is 0 till this frequency here, 10 to the power 3. We are calling it a, let's say, a 3 dB kind of a term here. Of course, it's not the 3 dB frequency of the entire transfer function. What we are saying is 10 power 3 is this breakpoint here, or corner point for this particular term here. And then after that, it changes at 20 dB per decade here. So that's this particular term. The third term is also very similar, except the corner part instead of being at 10 power 3 will be at 10 power 4. So it would look like this particular plot here. And this will also change by 20 dBs per decade here. So each one of those terms that you see here, first, second, and third, we separately sketch it out. And then all we have to do is now add it up, because the final magnitude of the transfer function is sum of these three parts here. So note that as I add it up, it's going to be, a constant line 20 dB still here. After this, this term comes into picture here, and my magnitude will start falling at 20 dBs per decade. Note that the third term is still 0 here. So it starts falling at 20 dBs per decade. Now this part also comes into picture here, and this will further cause an additional 20 dB per decade of fall here. So the net fall then starts to become 40 dB per decade here. Note that we are going from 1 decade. This is 10 power 4 to 10 power 5 is 1 decade, and it has fallen by 40 dBs here, from 0 to 40 here. Okay, so it falls by 40 dB here. So this is a simplified sketch of what this particular transfer function looks like. The magnitude part of it here. It remains constant till about 10 power 3, falls at 20 dB per decade till about 10 power 4. At that point, starts to fall at 40 dB per decade here. Okay, so that's the simplified transfer function. That's how we sketch it out, as I said. So the transfer function that we have sketched is accurate over most of the places except close to the corner points here. At that corner point, this one is an approximate curve. If we want an exact value, of course, at that particular point, we can go in and substitute and get the exact value also at that particular place here, right? So this is the approximate variation of the transfer function with frequency that we see here. And let me superimpose the exact function here, calculated here. So the blue one is the exact function, and you can see here that our approach of sketching the transfer function using these piecewise linear segments is a reasonable approach. It captures the magnitude part of the transfer function quite well here. Okay, so it's a simple approach and useful approach for seeing what my system is, characteristics of my system is. So this one, for example, we are seeing that frequencies up to 10 to the power 3 omega in terms of radian per second up to 10 to the power 3 are able to pass through my system, and after that my system attenuates those higher frequencies here, right? So you could say that in the term of filter, you could say this is like a low pass filter. It passes frequency up to 10 to the power 3 radian per second, and then after that it begins to attenuate it. And we'll see, you could say that the cutoff frequency of my filter is 10 to the power 3. Cutoff frequency would be 10 to the power 3 divided by 2 pi here. All right, so phase plots are also useful. So phase in this case, let's just look at a term like this. Phase is minus tan inverse omega by omega naught. Suppose you are given a phase, very simplified phase relationship. So to sketch this, we need to remember the plot is a little bit more complicated than the magnitude plot here. We need to remember three things here. The one is that as omega tends to 0, the magnitude of this quantity is 0. As omega tends to infinity, the magnitude of this quantity is minus 90 degree. And at omega equal to omega naught, the magnitude is minus 45 degree. So the actual phase plot looks like this here. So it has a curve of this particular kind. But we can see these 3 points here. At lower frequencies, we can see a 0 phase. At very high frequencies, we can see a minus 90 degree. And we can also see that at the omega naught, that corner point here, the corner frequency omega naught here, which is 10 power 4 here, is the phase is about minus 45 here. Phase is minus 45. So whenever you see a term like this, minus tan inverse omega by omega naught, it has a sketch of this particular kind here with these values here, asymptotic values here, low frequencies, high frequencies, and then a value at minus 45 degree, right? So when now more complicated phase expressions may have several such terms, and we'll have to combine them together to get the full phase plot here. All right, so let's continue with the sketching of transfer function. So we have h omega, which is given by, now there are 3 terms here. And so the first step is, of course, to write it out as 20 log 10 of magnitude of h omega and express it in terms like this. So 20, then the second term and the third term, and then there is this fourth term with a corner frequency of 10 power 5. And then our simplified plot of this is what we call as a Bode plot, and named after the person who made significant contributions to analysis of circuits. So our approach is, again, this is plot, y-axis is in dBs, x-axis is our radians per second. It can be frequency also, radians per second. And so this is on a log scale, right? So, and we start by sketching, first of all, each individual term. So 20 again remains 20. The second term, as we said, till about 10 to the power 3, we'll take it as 0. And then after 10 to the power 3, this term will change at 20 dB per decade here, right? So 0 and then 20 dB per decade here, right? So this is minus 20 dB per decade. The second term will remain 0 till 10 to the power 4. So it would look like this here. The corner frequency is 10 to the power 4 here. And for the last term, the corner frequency is 10 power 5 here, right? So we have each individual terms sketched out, right? So now what we have to do is add them up. So 20 dB still here. Then it starts decreasing at 20 dB per decade. This segment is contributing here. Now beyond this particular point, this segment also comes into picture. So it starts changing at 40 dB per decade here, decreasing at 40 dB per decade here. After that, this other segment also comes into picture. So it starts decreasing at 60 dB per decade here, right? So that becomes a sketch of the transfer function. It tells us, so again, we can see that, it's again a low pass filter, and the cutoff frequency of the filter is 10 to the power 3. After 10 to the power 3, it begins to attenuate higher frequencies. And the attenuation is changing with frequency. Between 10 to the power 3 to 10 power 4, the signal is getting attenuated by minus 20 dB per decade. But between here and here, 10 power 4 and 10 power 5, it becomes 40 dB per decade. And between here and here, it's even larger. It becomes 60 dB per decade here. Right? So higher frequencies are attenuated even more as compared to, let's say, somewhere here or somewhere over here. All right, so phase plot, let's look at in the previous case, we looked at only one term. Let's look at a 2 term here. So phase plot, the first term would contribute minus tan inverse omega by 10 to the power 3. The second one will contribute minus tan inverse omega by 10 power 4. And you need to sketch these out, keeping these in mind. That as omega tends to 0, phi equal to 0, omega tends to infinity, phi equal to minus 90. And omega equal to omega naught phi is minus 45. So it starts off, we can see here, it starts off at 0 here, close to 0. If we go to even lower frequencies, it will go to 0 here. And we know that as omega tends to infinity, this particular term will contribute minus 90, and this particular term will also contribute minus 90. So the whole thing should go at minus 180, which is what we see here. It's going towards minus 180. And in between is a more complicated relationship. For example, if you want to find out what is happening at 10 to the power 3. So at 10 to the power 3, this term, note that at 10 power 3, omega is 10 power 3. This term, of course, tan inverse 1 will contribute 45 degree. But this one will also contribute something here, right? So this one is not exactly 0. So that's why when we go to 10 power 3, you can see here the phase is around minus 50. So this is also contributing, okay? And similarly, if you go at 10 to the power 4, So when you go at omega equal to 10 power 4, then this term will contribute 45 degree, and this term 10 to the power 4 is divided by 10 power 3, so it's a factor of 10, so it's getting close to 90. So minus 90 and minus 45. So let's see, somewhere here you can see maybe it's getting close to 135 or so, right? So basically this is what we keep in mind while sketching the phase plot here. And note, in these cases we are sketching a qualitative variation with some quantitative values at maybe, let's say, in the beginning, towards the end, and a few places in the middle, so that we have a sense of how the phase is changing with frequency. All right, so what if you see a term like this? So this is not a complete transfer function, but what if you see a term like this? Well, if we take magnitude 20 log h omega, so this turns out to be 20n log 10 omega. And so if we were to plot it out, so this one will look like this here, with a slope of 20n dBs per decade. So if I change omega by a factor of 10, so this term becomes 1, and the magnitude changes by 20n. So that's why 20n dBs per decade here. So whenever you see a term like this, j omega to the power n, so the reason why I put 1 here, because I can write it as j omega by 1 here. So at omega equal to 1, this particular term contributes 0 dB here, right? And so if I had omega by 10 here, so at omega equal to 10, we would have had 0 dBs here. Anyway, so this is this kind of a term with omega to the power n here contributes a straight line with a slope of 20 n dBs per decade. And this is what we need to remember, that it intersects the omega axis, 0 dB point, at omega equal to 1. All right, so let's take a concrete example. Suppose we want to sketch the transfer function, the Bode plot of this particular circuit here. So we need to calculate the transfer function V0 by Vs here. This becomes 1 by j omega c, and it's easy. It's just like a voltage divider, so it's easy to write this out, j omega cr plus 1 plus j omega cr here. And note that we would like to express it in this form, j omega by omega 3 dB plus 1 plus j omega by omega 3 dB here, right? So because we know how to sketch 1 plus j omega by something here, and we know how to sketch j omega by something here, so that's why we take this one and cast it in this particular form. And omega 3 dB, of course, from this expression is 1 over RC, and frequency is f3 dB is 1 by 2 pi RC. Okay. And of course, if you want to sketch the plot, then you will take 20 log 10 h omega. So these are these two terms here, omega by omega 3 dB and 1 plus here. So let's sketch these out, and phases here. So let's sketch this out here. So 20 first term, remember first term, what will happen with first term here? First term is like this here. Note that it's a term here. So at omega equal to omega 3 dB, magnitude is 0 dB here. And then it increases at a slope of 20 dB per decade here. So this is this segment here. This one, it also has a corner point at omega 3 dB. But remember, we've already seen a term like this. So what happens is this term is 0 till about omega 3 dB. And at that point, it starts to decrease by 20 dB per decade here. So it would be like this here, minus 20 dB per decade. So now we need to combine them. So note that before this particular point, we have only this term there, this term here. So it would be like this here. And after this point, we have this term contributing 20 dB per decade, this term contributing minus 20 dB per decade. So they cancel each other out. They cancel each other out. So it's constant here, 0. Right? So this will become the sketch of the Bode plot of this transfer function here. Okay. So, and this we see is a high pass filter. Why? Because 0 dB means here that output is, the input is simply passing through my circuit here. V0 by input, V0 by Vin is 1. That's why it is 0 dB. And lower frequencies, note that are getting attenuated, because it's, as you go to lower and lower frequencies, the attenuation becomes higher and higher here. And that's why we are calling it high pass filter. Passes high frequencies, but attenuates lower frequencies. And with a cutoff frequency of omega 3 dB here at this particular point. Right, so as a concrete example, suppose I take 1 microfarad, R1 is 0.159K. So the frequency, cutoff frequency becomes 1 by 2 pi RC is 10 to the power 3 Hertz. And these are simulation results, so you can see the exact plot here. And this is our approximate plot, right? This is what we just obtained, approximate plot, and this is the exact plot. And we said that, we are not sketching things very well at this particular point here. So you can see that our cutoff frequency is 1K here. So at this particular point, what will be the magnitude here? Minus 3 dB. Please verify it that if I substitute numbers there, this will be minus 3 dB at this particular point here. That's why many times we call these frequencies as 3 dB frequencies, cutoff frequencies. They are the point where it's 0 dB, and then at this particular point becomes minus 3 dB. This is where we have this 1 over 2 pi RC. All right, so let's take a transfer function with a variety of segments. There's a k, there's a j omega by omega naught n, j omega by omega 1 r, plus 1 plus j omega by omega 2 m, plus 1 plus j omega by omega 3 t here. So various terms are there. And so in general, what would you do? Well, you'll take each individual term. If you take k, then it will be 20 log k. Right, so it would be of this particular form here. So a term like this in dBs will be 20 log k. If you look at this term here, omega by omega naught, well, this term, because it is raised to the power n here, so it would be, it will intersect here at omega naught, and it would be increasing at 20 n dB per decade here. Note that it's in the numerator here. Then if you see a term like this, j omega by omega 1 r, let's say omega 1 is at a higher frequency. So because it's in the denominator here, so this one will be going like this here with a negative slope here. And at omega 1 and 20 r dB per decade, it would be decreasing at this rate here. And this particular term here, we've already seen how to sketch this. So till omega 2 it is 0, and then beyond that it now, because it is raised to the power m, is minus 20 m dB per decade here. And this particular term will be till omega 3 const 0 here, and then it will increase at 20 t dB per decade here, right? So each one of these terms can be individually sketched, and then of course you can combine them up together to get the final values here. So let's practice once more. So let's say you're given a transfer function like this here, 200 j omega 1 plus 10 plus j omega 100 plus j omega here. So the first thing is that you should cast each term in the form that we have shown here. J omega by omega naught to the power n, 1 plus j omega by omega 2. Note that 1 here, and similarly 1 here, right? So cast it in this particular form here. So this 10 plus j omega, so what we'll do is we'll take 10, factor 10 out. That's why it becomes 1 plus j omega by 10 here. We'll take 100 out, so it becomes 1 plus j omega by 100 here. And this term is j omega by 1. Right, and then combine all those factors that you took out, combine them into one single term. Right, so we have now 4 terms here, 1, 2, 3, 4, and each one of them you have to sketch it out. So the first one, take 20 log 10 of 0.2. So I think this is minus 14 dB. So that's this particular part. This part j omega will be like this here. It starts from because we can write it as omega by 1. So it intersects the 0 dB point at 1. This is at 1 radians per second 1 here. And it increases at 20 dB per decade here, right? Because it's omega to the power 1 here. So it increases 20 dB per decade here. The third term will be, we have seen this third term here. So it will be 0. And then at 10 radians per second, it will decrease like this here. And then the fourth term, it will decrease in this particular manner here. So let's combine all of these terms together. So we have starting here. So starts from minus 14 dB here. And we add this constant term minus 14 and this together. So it increases like this here. After this is increasing at 20 dB per decade. This is decreasing at 20 dB per decade. So they cancel each other. So it becomes constant. And then this term comes into picture here. So it starts to fall at 20 dB per decade here. So that's the approximate sketch of our transfer function of the form which is shown over here. And let's see how it compares with the actual one. So this is what we sketched. And if we calculate the full transfer function, putting in exact values there. This is how it looks like here, the blue one that you see here. Right, so as I said, there are some errors here at this particular point here, at this point here. There are a few errors that you can see here, but our method captures the sketch of the transfer function quite accurately, and we are able to see what this particular circuit is doing. In this case, we can see that it's attenuating lower frequencies, lower and lower. I've not gone below this, so lower frequencies are getting attenuated. Higher frequencies are also getting attenuated. In between, there's a band of frequencies which is passing reasonably well through my circuit here. So, we would call something like this as a band pass filter. It is passing a band of frequencies here, a band of frequencies in the middle. Lower frequencies is rejecting, higher frequencies is rejecting, but there is a band between lower and higher, which it is passing with relative ease, compared to lower and higher is passing with relative ease here. All right, so we've been talking about filters, and these are 4 broad classes of filters. We are plotting the transfer function, magnitude of transfer function as a function of frequency. So we could have a qualitative behavior like this here, and it's obvious that it's passing low frequencies here and attenuating higher. We could have a behavior here, so we would call it a low pass filter. This one, it's passing higher frequencies, rejecting lower frequencies, so we would call it a high pass filter. And we just discussed this, is passing a band of frequencies, rejecting lower and rejecting higher, so we call it band pass filter. And this one is rejecting a band of frequencies, is rejecting it or stopping it, we call it a band stop filter. Higher frequencies is passing through, lower frequencies also passing through, but there's a band here which it is rejecting. Right, so we call this a band stop. So 4 broad classes of filters that are there, and each one of them has a lot of uses in different applications, and some of them we may see later on. Okay, so as an example, this RC circuit that you see here, this R and C, you can calculate the transfer function. It has this particular form here. When you have an R and you have a C here, it acts as a low pass filter. When you put a C here and an R here and you take the output across the resistor, then it acts like this here, and then it acts like a high pass filter. Right, so how do we quickly, by the way, before we do that, how do we quickly tell whether a filter is high pass or a low pass? Note that the cutoff point is important. It's passing a range of frequencies and then it begins to attenuate, right? So there is a transition point, the corner point or the 3 dB point that we are talking about. So 3 dB frequency of single capacitor filters, we've calculated this earlier, is simply equal to 3 dB will be 1 over 2 pi RC. Now, if we have a circuit which consists of, let's say, 2 resistors and capacitors is more complicated, well, note that, we can take all the other resistors and, we could build a Thevenin's equivalent across the capacitor. If we build a Thevenin's equivalent across the capacitor, then the capacitor is seeing a net resistance, right? The Thevenin's resistance. And in this case, the net resistance that the capacitor sees, so you can take R2 over here, and the net resistance that the capacitor sees is R1 parallel R2. And so this circuit is also like this. The moment you build a Thevenin's equivalent across the capacitor part here, it's also like this. And therefore, this one also behaves as a low pass filter with a cutoff frequency R1 parallel R2 times C. So in general, if you're given a linear circuit and with one capacitor here, you could always transform this particular part into a Thevenin's resistance and a voltage source. And if you're taking the voltage across the capacitor here, it would look like a low pass filter with a cutoff frequency of 1 over R equivalent or R Thevenin's, whatever you would like to call, the net resistance that my capacitor sees here. So the resistance that the capacitor sees is R equivalent or R Thevenin, and that would be my cutoff frequency here. Note that this is related to, when we did transient analysis, the time constant, right? So the two things are related together. So as I just mentioned earlier, one can often tell the type of filter by looking at the behavior of the circuit. If you want to tell, is it low pass, high pass, band stop, what kind of a filter is it? Well, you look at the behavior of the circuit at very low and very high frequencies. And you keep in mind, while you're trying to understand circuit at very low and very high frequencies, that capacitor offers very high impedance at low frequencies, right? 1 over omega C, and very low impedance at high frequencies. And you keep that in mind. So let's take this circuit. So at low frequencies, very low frequencies, the capacitor would practically act as 1 by omega C here, will act like an open. So, so qualitatively we say, well, the capacitor is like an open. And so we have a circuit like this. Now, if we have a circuit like this, now we can easily see that V0 will be equal to Vs. V0 will be equal to Vs. Fine, low frequency. Then when we go to high frequency, we said capacitor will act like a short, 1 over omega C, right? Impedance. So capacitor, we replace it by a short here, and V0 is equal to 0. So when we see this behavior, low frequency is Vs and high frequency is 0 here. And then we look at this diagram here, which diagram sort of tells us this kind of a behavior. We can clearly see that our behavior is like this here. Low frequency is here, and higher frequencies is some low value here, right? Some highly attenuated signal here. So we can see that this circuit is like a low pass filter. Okay. This one here, low pass filter, right? So what about this? Okay, how do we analyze a circuit like this? So in this case also, what do? We look at low frequency. So low frequency, what will happen? The capacitors will act like open. So the circuit acts like this here. What will happen to V0? V0 will be 0. Right, so Vs here, this is open, no current in R2, this is 0 here. All right, what about high frequency? Well, high frequency is capacitors act as short. So this is a short, this is a short. And what happens to V0? Because this is a short here, so V0 is again 0. Right, so I'll leave it to you. What do you think this circuit may act like? Okay, so let's look at so if somebody looks at a diagram like this, and so it looks at a band pass filter like this here, right, which is passing a band of frequencies. It may give an idea that maybe if I have a low pass and a high pass filter, maybe I can build a band pass filter by combining them, right? So for example, this segment that you're seeing here, I can see that there's a segment like this here, right? And then this part here, the falling part, I can see a part here. So you may think, well, what if I take a low pass and a high pass filter and I combine them together? Like this here, right? Like this here with a cutoff frequency F2 here and a low pass here to give rise to this segment here with a cutoff frequency of let's say F1 here, and F1 is greater than F2, right? So if we do that together, then maybe I can get a band pass filter, right? Okay, so how do I create something like this? We've already seen that a high pass filter can be made through an RC filter, simple RC circuit, provided I take the output at across the resistor. And we also said that we can make a low pass filter like this using another RC circuit, provided we take the output at the capacitor. So what if we combine them together? Capacitor and resistor. So this part, the goal is that this part may result in something like this here, and R and C may result in something like this here. Now, of course, it's not as simple as this, because what happens is this part and this part together, they're all connected together, so they all influence each other. So things are a little bit more complicated, but qualitatively the circuit is likely to behave like this here, that this part is going to contribute to a high pass part, and this part is going to contribute to a low pass part here. And if we choose the value of R2, C2, R1, C1 properly, you may get a behavior like this. So let's see an example here, right? And approximate values may be, this is keeping in mind that the two circuits R2, C2 and R1, C1 do not interfere with each other. In practice, they would, so that's why it's an approximate value here. But let's see how the two circuits, as an example here. So this is C1, R1 here, this is R2, C2 here. And note that we wanted the low pass frequency to be higher here. So R2, C2 time constants, C2 has been chosen to be 100 times smaller than C1. So that would ensure that the time constants are 100 times lower and frequencies are 100 times higher. So we combine them together and we can see a band pass kind of a behavior here, right? So this is just in a simple way trying to illustrate that we can, by taking elementary sections like this here, a high pass section and a low pass section, we could combine them together and build more complex filters. We could have also taken, for example, two low pass sections, an R1 C1 and an R2 C2, And both of them are low pass filters, so both of them would have combined together to give us another low pass filter. And you can check it out through some by sketching your own Bode plot, that particular filter would have provided you with more attenuation in the band in which you don't want frequencies to pass. So it would have been that way a better filter, a filter which attenuates the unwanted frequencies, maybe a better filter in that respect here. Well, suppose we want a band stop filter here, right? If we want a band stop filter, then would this, can we, we are seeing a segment like this here. We are seeing a segment like this here. So could we, by combining them, obtain a band stop filter here? What if somebody suggests take a low pass filter and take a high pass filter here? This will give this segment, this will give this segment. Do you think we can combine them up to get something like a band stop? Or is there a flaw in this particular logic? Think about it. Okay. Let's look at another circuit. So if somebody, let's say, has designed this particular circuit, so a parallel RC circuit here and a series RC circuit here, and we would like to figure out what does this circuit do. So our method is, at least it would give us some idea of what the circuit does. So by looking at these two behaviors, low frequency behavior, so capacitors will be open. So we open the capacitors out, and then we analyze the simplified circuit. So we see that V0 is equal to Vn. V0 is equal to Vn. Okay, all right. Higher frequencies, capacitor, let's short it out. All capacitors short here, short here. Well, at higher frequencies, so this gets shorted out. So V0 becomes equal to Vn. So that's interesting. At lower frequencies is V0 equal to Vn. At higher frequencies is also equal to V0 equal to Vn. And in between, we know that, this will have some impedance and this will have some impedance here. And so this voltage will get divided between the two impedances. And V0 will not be equal to Vn. V0, magnitude of V0 may be less than Vn. Right? So in between it is less. So, but at low frequencies is Vn. At high frequencies is also Vn. But some intermediate frequency is going to be smaller. So what will it do? Well, lower frequencies is like this. So these are simulation results. Higher frequencies like this. And at some intermediate frequencies is smaller, right? So this begins to look like a band stop filter, right? It's attenuating some band of frequencies here, and may not be a very good, see, if it would, we would call it a very good filters if the boundaries are very sharp. That's why, when we have drawn here, if we go back and we've drawn here, this filter would be ideal filter here if it were constant, and at this particular point it abruptly drops to 0 or very, very high value here, right? So this is not so gradual, but is so that it attenuates or rejects all the unwanted frequencies and perfectly passes all the wanted frequencies, right? So that would be an ideal low pass filter, a rectangular like this here. An ideal high pass filter would be constant here and then abruptly drops here, right? The more gradual the attenuation, the less useful is the filter in attenuating the unwanted frequencies, right? But it's not easy. You can see that a simple RC circuit attenuates at a rate of 20 dB per decade. And if I build two RC circuits, maybe it does 40 dB per decade. Now, if you want 100 dB per decade attenuation, well, you will require many RC circuits, or you will require some other approach. That is here. Okay, so let's... so before we finish our discussion today, let's look at, we've been looking at the capacitive RC circuits. Let's look at RL circuit here. So how does an RL circuit behave here, R and L here? Well, again, we can calculate the transfer function, keeping in mind that this is j omega L, and we write down the transfer function. We can cast it in this particular form, and the omega 3 dB is R by L here. And this behavior, what j omega by omega 3 dB plus 1 plus j omega by omega 3 dB here. So this is in this particular form here. So this acts like a high pass filter. Now, does it make sense? Well, let's look at it at low frequencies. What will it do? The two asymptotes that we talked about, low frequency behavior and high frequency behavior. So at very low frequencies, this will be a short, and therefore V0 is 0. While at high frequencies, this impedance is going to be very high, and almost going towards infinity, and therefore all the voltage will appear across this. So we can see high frequencies is here, V0 will be Vs, low frequency V0 will be practically 0. So it's a high pass filter. So we can see that from the behavior here, and that's what we get from detailed analysis of the filter here. All right, so high pass filter. So let's remember, so this is L is here. Now if we switch L here and bring R here, what will happen? Well, the opposite behavior, it will become a low pass filter. So you can calculate the transfer function and plot it out, and then you see it's a low pass filter here. So an LR circuit also acts as a low pass filter. RC circuits can also be used as a low pass filter. We can combine L, R, and C and get very, very interesting behaviors. We can build, for example, very nice band pass filters by using LCR circuits. So that's what we'll see in the next lecture. So let's stop here.